now I can start recording. So welcome back, folks. Let's see here. We have formative assessment number 5, I think. The TAs are going to lead us through that in just a second. I have, let's see, nothing is due next week. Next week is the university fall break, so there are no classes, no office hours, and hopefully we can all take a minute to catch our breath before we dive into the rest of the semester. But in case you're stuck here and you have nothing to do and you get bored, I put your next homework up, and the TAs have checked it and done it, so they're prepared to help you.
Yay.
That is not due until December 9th, so if you're like, please don't talk to me about homework, that's fine. But if you're one of those folks who wants to work ahead and get your stuff done because you're preparing for other finals or other things, that's totally fine. I hope to have your last homework up by the end of break for sure, and hopefully before then. So homework 5 is based on example 4B, and to make it comparably difficult across classes, I made it a hierarchical assignment, meaning that I have a predictor, say what happened, add another predictor, say what happened, add another predictor, say what happens, because that code is a lot less laborious than having everything in one model and then having to estimate comparison models. So state of folks nest reg will do your entire homework like in one thing, like one line of code. Wow. So it's relatively code free, this one, and the focus is much more on understanding how the results differ across models and how to talk about changes in effect size and that kind of stuff. So it's longer, but it should be mostly review at this point. And your very last homework will be based on interaction terms, what we're talking about right now. So how's that sound?
Perfect.
Perfect. Enthusiasm for homework. That's wonderful. All right then. Let's see. So Sam and Erica, if you want to hop on up here, I'm on Zoom, so I can let people in, and just try to pay attention to the chat and the faces. I know that's tricky, but this is part of your teacher training. You're learning how to work a hybrid class. So exactly, it's fun. And I'll sit over here.
Okay. Hi, everyone, on Zoom and in person. So I'll be going over questions 1 and 2. So to start, in what situations would you expect the unique effect of a predictor's slope to differ from its bivariate effect? Can anyone give me a guess or an answer if you're confident with it?
Lots of good answers today.
Lots, yes.
Kind of interaction.
Mm-hmm.
Mask some of the.
Yep, we talk about suppression. One of them, yes.
So the unique effect differs from the bivariate effect when other variables influence the predictor.
And when there's correlation between the predictors as well, right? When we're talking about, that was one of the ones that we noted across people's responses was when predictors are correlated, the unique and bivariate effects are going to differ, right? Because the unique effect is looking at, after we control for other predictors in the model, how much is this variable actually contributing to our understanding of the outcome, right? And the bivariate effect is not taking that into account, right? So when you have variables that are correlated with one another, right, that unique effect and bivariate effect are going to differ, because when we think about our Venn diagram and the overlap, that overlap is getting bigger for some, and that bivariate effect is or that unique effect is going to be less because there's more of an effect that's overlapping between. I'm sorry, Zoomers, if you can't hear me, my arms are up in front of me. I don't know if you can hear me. Just muffled. I know. I moved it up a little bit. Yeah. So when predictors are correlated with one another, that was one of the main things that we noted across people's responses. Is when unique and bivariate effects are going to differ. Do you have a question, Usman, or?
No.
Yeah, just trying to comprehend it. Yeah. Processing.
Yeah, process.
Awesome. Okay, are there any questions about question 1?
If I can add one.
Yeah.
So several folks mentioned suppression, and that can only happen if your predictors are correlated. So predictors being correlated is the main idea, and then the ways in which they're correlated can turn out to yield different answers for the relationships when they're together than when they're separate. So
screen in the chat, that's all.
Nope, I got the doorbell. There's
Awesome.
only so much multitasking I can ask.
Right, exactly. Especially with the screen, I'm like, oh my gosh, there's so much going on. Okay, so question 2. What is the difference between semi-partial and partial eta square effect sizes? Let's start with that first one. Can anyone tell me the difference between semi-partial and partial eta square effect sizes?
I'll kick us off with the denominator, but I'll stop there and let somebody else go forward.
There is a difference in the denominator, yes. What is the difference in the denominator? Anybody have a thought? I know Michael has a thought.
Lots of good answers.
Got one?
The semi-partial has, let me make sure I'm reading this right, sorry.
Yeah, yeah.
It has all the variance in the denominator for the semi-partial
Yep.
when you're creating that, whereas the partial eta, it has the variance only for it over its only plus whatever's not accounted for by the other variables that you're using in your model.
Bingo. Could not have said it better myself. So yes, so the semi-partial eta square effect size is looking at the unique contribution to the R squared, right? When we're talking about R squared, we're talking about the unique contribution of a predictor to the overall R squared, or the overall model R squared. When we're talking about the partial eta effect size, we're talking about what's left over, right? And so when we look at that second question of which one can be artificially increased by adding more predictors to the model, the partial eta effect size can be modified by adding more predictors, right? Like Lisa talked about, if we have 10 predictors in a model, right, that residual variance is going to be less, likely, very likely, it's going to be less than if we have only 5 predictors in a model. And so that partial eta is going to be different because we're not talking about the total variance anymore in the denominator. We're talking about that residual variance and what's left over, what's left over with that model, right? And so because that partial eta square effect size can be modified, that we also cannot compare across models when we're talking about the partial eta. Right? With the semi-partial eta square, we can compare across studies, we can compare across models, but with the partial, because we're talking about what's left over, and because that can change depending on how many predictors we have in the model, we cannot compare across models or across studies. I'm trying to see if I had any... Oh, another note that I kind of took from what Lisa had talked about was, if you're chasing an R squared, right? If we're trying to maximize our R squared value, that's where the partial eta, you can kind of cheat the partial eta. And so that is where Lisa's not as big of a fan of the partial eta squared, because in a way you can just keep throwing variables at this model, and if you have 20 predictors in the model, yeah, your R squared is going to be fantastic, right? But like we talked about a couple weeks ago, if you're just doing that to see which people are going to buy your product, well, power to you, that's fine. But if you're actually, a social scientist and you're trying to, have a theory-driven research question, and you're including people's favorite color to determine how many classes they're going to take or what their graduation rate is for across a university, you're just chasing that R squared, right? You're throwing the kitchen sink, as some people call it, at the model, and you're going to be able to cheat that partial eta square, whereas you're not going to be able to cheat the semi-partial eta square by adding more predictors to the model. Any questions with question 2? Awesome. All right. Question 3.
Yeah, moving on to question 3. Trying to find the mouse.
Oh yeah, I tried it.
Mouse thing just kills everybody. I'm like the only one who can work it.
I tried going that way and it didn't want to work. Okay. Just consistent entertainment for you all trying to find the mouse. Okay, so talking about effect sizes going into R squared now, how do we determine the significance of the model R squared? zoomers, roomers, how would you, in what part of your output would you tell that your R squared for your model is significant? Start with an F-test, yes. So on your overall model output, you should have the F-test, and that will tell you whether or not your R squared is significant. And then when might we want to see the change in R squared?
When you want to see if adding more predictors improves the model's ability to account for the variance.
Yeah, so adding another or other predictors. So then going into the last part of the question, when would we need extra steps to generate that additional F-test that's not directly given by the model? You had good answers for this, so I know you know it. Yeah.
Small samples?
Think less of the sample and think of the predictors themselves. Specifically, a hint like the number of predictors. If that helps jog anyone's memories. So how would you tell if you added one additional slope, how would you tell if that change in R squared is significant?
Welcome to my world.
I know.
Take pity on her, come on, that's my question.
If your test on that additional item was significant, then if that was significant, then the change was significant.
I would say slope instead of item,
Slope.
but yes.
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 Good, yes. Your
And,
slope.
and then what happens if you're adding more than one slope? When you're looking at the change in R squared.
You have to do like a separate test.
Yes, so that's when you would need the separate F-test if you're adding multiple slopes to see that combined contribution of the change in R squared. Yeah, see, you know this.
Yay.
Any questions from anyone? Anything I missed? Okay.
Yay.
Yeah,
Nice job.
that was me. That's right.
You left.
Yes, I left the building, but that's just because I don't need to be on Zoom twice. So yes, good job. I want my share back, because I've earned the right to sit down. That's why I got my degree. Remember, no name tags, no work shoes, and sitting down. So I had an idea, actually earlier today, that I wanted to reinforce. We're going into paint here.
Pictures.
Yeah, pictures. The partial eta square versus the semi-partial. And by the way, semi-partial is also called part. So it gets even worse. So then you can have part and partial, which is like a saying, but it's not spelled the same, I don't think.
I don't think so either, but yes.
Okay, so I'm not drawing an X and a Y axis this time. I'm going to draw a circle. Okay?
It's a good circle, actually.
Let's say that this is one of those giant cookies that you can get like from a bakery for someone's birthday. And it says happy birthday on it. Okay, so you bring the giant cookie to someone's birthday at the office. And let's say that the people at the office eat half of it. So this is all gone, okay? Cookie's all gone. And you bring it home and you let your kids have at it. And then one of your kids decides they're going to eat a whole bunch of it. There we go. How much of the cookie did your kid eat, to the best of my drawing ability here?
A quarter of the original.
So here's the thing. I look at this and say they ate a quarter of it. They ate 25% of it. That's what I intended to draw at least. That's semi-partial. Out of the whole, how much did you get? Another way to look at it is, well, they got half of what was left.
Mhm.
That's partial. So did your kid eat half the cookie? Not really. They ate the half that was left over.
Half of that.
So that's the difference in effect size. Now, what if at work the people scarfed up a whole lot more?
Mhm.
And your kid still likes cookies. And so they ate as much as they possibly could.
So they eat the rest.
Yeah, so how much did they eat? They ate the whole thing. That's partial. Or they ate a quarter of it. That's semi-partial. So this is the idea of stacking the deck, adding additional predictors that explain additional variance. Your relative contribution looks bigger if there's less left over. So I'm less of a fan of partial for that very reason. I like semi-partial. And I like cookies. Although, my son really likes cookies. I would save them for him. All right. Let's see. I think that was all I was going to say about that. So in terms of this, we're going to do more on this idea in the example that we have. But in terms of distributions, T is a distribution that's used to test one slope. F is a distribution that's used to test more than one. The difference in terms of what this question is motivating is getting you to recognize when the F is provided for you and when you have to go to an extra step to ask for it. In this class and in the models of this class, F will always be provided for the R-square. That is a joint test of all the fixed slopes that are in your model. In other classes with other models, that will not be the case. You may have to actually ask for it as a separate piece of information. So for now, it's done for you. But if you're adding them, if there's only one, the p-value for that t is the test of whether that one contributed. If you're adding more than one, then we have to generate a second f, as we said. So that's what we get to do. Would you like to see an example?
Yes.
Example 5, the last one of the semester, and this one's only 20 pages. So, well, it's fair, because this is what I would call a single level model. And my morning, the class that's above this, not in the morning, but earlier in the afternoon, has 2 level models, and their last example was twice this long. So it tracks.
Twice the fun.
Yeah, a 39-page example we started today. This one's only 20. And this is, I'll show you where it is. Scrolling. Hang on, I went too far. That tends to happen. For homework 6. Okay, there's your signpost. Look at this one.
Hint.
Yeah, I'm not even going to cough or anything. I'm just going to say this. Look at this model as a template for you to follow. It will match the closest to what you're going to do for your last homework. But I have other examples in here because life isn't just about homework. Life is about having the skills to answer any kind of research question. So we're talking about interactions in this unit. What are they for again? What's the point of including a multiplicative combination of predictors as an interaction term? What are interaction terms used for? Looking for one keyword that starts with an M.
Moderation.
There we go, moderation, yes. Now, what does moderation mean? In this context, moderation might mean don't eat all the cookies. But in this context, it means something different. I'll take gestures. Words, gestures, pictures, anything you got. I'm patient. I'll sit here. It's fine.
I'm patient too.
I'm contractually obligated to be here. Influence of another variable? Yeah, I would say that.
Mm-hmm.
It's the idea that a relationship between two variables depends on some other variable. You can't just say x is related to higher y always. Well, maybe for some people, x is not related to y, and maybe for other people, it's related to not y. And it goes in the opposite direction. So it's the idea that a relationship between two pieces of information may depend on a third factor. That's the big picture. And moderation questions are very, very common, which is why I want you to have all the tools to be able to answer them, regardless of what kind of variables you have. So one thing that I still occasionally see folks do is, in order to test moderation, take a continuous variable and cut it up into like high and low, so that you can see if people who are high on this have a different relationship than people who are low on this. Please don't ever do that. Cutting up continuous information reduces the information that you have and introduces measurement error. It's because of the world of ANOVA that people think they have to do that, because ANOVA has interaction terms built into it as a default setting, whereas regression does not. But in reality, it is up to you what kind of variables you have and how they interact in order to answer various kinds of research questions. So from that perspective, I deliberately have examples of continuous by continuous, continuous by binary, and binary by categorical, so that you can have all the different combinations of variables and how to do it. So this example is following up on example 4b. So these are the older adults. This is fake data, but it's based on real data. So the story is we're predicting cognition, which is measured as a measure of crystallized intelligence, known as the information test. It is being predicted from the age, which is going to be centered at 85. These are older adults in the story. Grip strength, which is a proxy for physical function, and that is measured in pounds per square inch, in which 9 was near the mean of the sample. I have a binary variable for we have men versus women, where men are the reference, and a 3-category dementia diagnosis predictor, whether they're never going to have it, they will eventually get it during a subsequent aspect of the study, or whether they currently have it. So spoiler alert, dementia is bad for you. But do you think it's differentially bad for you based on other things? Could be. Is getting old bad for you? I would say so.
Leads to death.
It can. Do you think some people have a better experience aging than other people? Uh-huh. So yeah, like all of these variables, like this is a fairly straightforward story, but I can easily think of, oh, well, this matters more in some people than others. And that idea, that's moderation. So we have examples of various kinds. So any questions on the setup? Okay. So the exact same code is used here to create all the variables that we need, as in 4b. I included it for completeness, but there's nothing new here. So we're centering age and grip strength at constants, and I picked those constants based on the distribution of those variables. Those are near the means. I am taking my 3-group dementia variable and turning it into 2 binary predictors. This is indicator coding. So the reference group is going to be group 1. They're going to have the 0 values for both of the new predictors. Group 2 is going to be controlled by DEM-NF. So this is none versus future. Future is the second group. And then NC stands for none versus current, and that's going to be used to identify group 3. Labeling everything, and then removing cases that would have any missing information so that my sample stays constant. That is not the best way to deal with missing data, but it's what we have for now. Take more classes if you'd like to learn better approaches to that. That's what I would have. Our folks, everything is the same for you, centering my quantitative predictors, creating my dummy codes, and then selecting complete cases for the variables in the story. I have functions to automate things, as usual, and I fixed the p-values. So they're not in scientific notation anymore. Thank you, Jonathan. I give credit where credit is due. It's like Sprint F or something, is what he told me it was called. It was one word, and he knew what it was, and I was never going to find that in the Google, so I just had him fix it for me. So my first model here, I'm calling main effects only. That terminology means no interactions, meaning just an additive model where each predictor contributes by itself. And the research question that would be answered by this would be, how do age in years, grip strength in pounds per square inch, binary sex, and 3-group dementia uniquely predict cognition? That's my question. So this is the ending model of example 4b, just to refresh you. There's one linear combination that I would potentially be interested in here, and that is the difference between future and current. So beta 4 here is going to tell me how none differs from future, Beta 5 is going to tell me how none differs from current. I don't know about future versus current, but I can subtract the two. So this is the adjusted mean for the current group. This is the adjusted mean for the future group, and then the difference right here gives me the contrast of future versus current. So that means that beta 4 would need the -1 in the code, and beta 5 would need the 1, as we'll see later on. All right, I have, let's see, do I have both sets of output? Yes, I do. Yes. I have to remind myself what I'm doing. Okay, so state of focus first. I try to put it in the same order so that it's clear which code goes with which package. So here are my 5 predictors. I am storing the results of the model. So my naming convention here is model main for main effects. I'm printing that and then saving the sums of squares from this model because I'm going to need that to do effect sizes. And no bolding of the results here because I'm taking the training wheels off. So things that I would pay attention to. Where's my residual variance?
.07.
Yeah, so if I had to put words on that people would understand, can you tell me what that means conceptually? What does 88 mean? It is residual variance. It is mean square residual. It is mean square error. But what's it mean?
Would we say that that's the amount of variance that's not explained by the model?
Ding, ding, ding. The amount of variance that is not explained by the model.
Per degree of freedom?
Nope. Just our, yeah, its variance is already per something.
Oh, sorry.
Yeah, so like this is the, I would say this is the amount of, like, I'll say information for, it's the numerator of variance.
It's understood as per.
Yeah, and so then you divide sums of
Right,
squares by
right.
denominator degrees of freedom, and then that's your residual variance.
So it's
Yep.
understood per. Okay.
Yep, so that is the
No
amount
problem.
of leftover variance in cognition, the
Mm-hmm.
outcome variable. Now, how much did it used to be? Do I know that? If this is the leftover part, what was there originally? Is that on my screen somewhere?
That'd be the 120.
Yes, it is. That's what it used to be. So here's what I got. Here's what's left. Here's the total. So I have like 88 left out of 120. Is there like a way that I could think about that like proportionately? Hint, hint. Like maybe it's related to this thing over here. R square, is that the amount explained or the amount left over?
Explain.
Explained. So 0.2773 is the proportion of the total variance that's been explained. 1 minus that is what's left over. So there's an asymmetry here that can be confusing. 88 is the amount that's left over out of 120, but we're focusing on the rest of it. 120 minus 88. 27% of it is explained. So we typically report R square, 0.28. Does that sound like a lot?
Depends your context.
It depends on the context. Is it bigger than 0?
Yes.
How do I know that?
My probability of F.
Plus
Yep.
0.
Yep, those two, yep. Why is my F numerator degrees of freedom 5?
It's got 5 variables.
5 slopes,
I,
yes. And I'm
But then
saying,
those variables are different, right?
yes, but it depends on your definition of a variable.
Okay.
So if I think of this as, these are 5 variables, right? There's 5 slopes.
Yeah.
But I'm also sort of thinking of this as one variable in my head because it's dementia group.
That's
So,
5 slopes.
Yeah, it's 5 slopes. Technically 5 variables because we made these 2 new variables, but conceptually I'm thinking of it as 4 predictors. 4 characteristics of a person, I would say.
Got it.
Yep. So yes, F is per slope. It's a ratio of how much information we have explained relative to what's left over. So 1 would be like the neutral point. Ours is 42. So yes, definitely greater than 0. And we go down into the results. I labeled these for you. So these are the betas here. We'll do the results on the R side, try to keep it fair. Here's the missing contrast. So DEM NF versus NC, each of those is relative to the none group, and this one is relative to the between the alternative groups. Question?
Can you remind me the F test, the number it being 40? Like, what is the range of F? Like, what are we looking for?
F is a distribution
Right.
that changes its shape based on the 2 degrees of freedom. So it's always going to be positive. It's in a squared metric. It is positively skewed, so it's kind of like humpy and long like that. And the critical value would be the point on the distribution where 5% of it is beyond that point on the right. So you can't know just by looking at this number what it means. That's the short answer. It depends on the degrees of freedom. The good news is that you don't have to know, because the whole point of getting the F is to get to the p-value for it. So essentially what this is saying is that if these 5 slopes were garbage, like how frequently would we get an F this big? And the answer is 0 to at least 4 decimal places. Sure, good questions. Ding ding. Okay. So this -1, 1, I had at least 1 or 2 questions about this over email. This has to go in this order to get the sign right. So it's, if you want to know future versus current, like future is the reference for the comparison, and you want to talk about how current differs from future, then the first one gets the -1 in the code, and the second one gets the 1. So that's why down here, I have the first predictor multiplied by -1 for future, and then current gets the 1. Now, if I switched these, I will get a positive 10 instead, which the homework system will not take. So I have it labeled very specifically as this versus this. The first one gets the -1 in the code to get the sign right. All right, our folks, here's your table. This is from the Supernova package. I like this because this is how every other software package presents these models, so it's nice. Where is your error variance in this table? Residual variance.
Across from error under MS.
Yeah, it's the last row here. And where is your R square?
Top line, PRE.
Yes, proportion reduction in error for the model. That's your overall R square. The rest of these, by the way, are partial eta squares. So they're dead to me. You didn't get the whole cookie, all right? You only got a quarter of it. And let's see here. Yeah, there's the 120, so that's out of the total. Look, look! I fixed it.
Beautiful.
See? The p-values, you can read them now. It's very exciting. And there's just less than 0.001 rather than scientific notation. Very excited about this. So let's go through these. The intercept, 29, is the expected cognition outcome for what kind of person? Let's go through the list. Someone who is.
85.
Who can squeeze
9.
9 pounds. And is a dude or a chick?
Both.
We don't have that category. This is a old
That's on the
school
B table.
binary version. Men
A
or
dude.
women?
Because they're 0.
Yeah, the men are the 0.
Right.
So yes.
Yeah.
Men are the 0. And same idea here, the N group for dementia, which stands for none. So that's my reference
They'll never
point.
get it.
Now what happens if you are older to your cognition?
Yeah, minus.
Minus. Minus 0.4 per what?
Year of age?
Per year of age.
Over 85.
Uh,
Or actually, year of age period.
Yeah, so it's period, because
true.
this is a linear
Yeah.
slope. We don't have a quadratic slope, and there's no interaction terms in this model. So for every year of age, whether it's going from 20 to 21 or 100 to 101,
Don't matter.
cognition goes down by 0.4. And we had tested a quadratic slope for age in example 4B, found we didn't need one, and so we left it there. So at the beginning of the semester, I said that a slope is the change in y for a 1 unit change in x, right? That is still true. But now we're putting the words in the problem, because you can't write that in a results section and have people follow you. This is the change in cognition per year of age. Put the units and the variables in the story. And it is significant, hooray. Unless you're old, in which case, maybe not hooray. But how about grip strength? What happens if you are stronger?
Cognition increases.
Yeah, cognition is higher. So in people who are stronger, cognition is higher. Specifically, per additional pound you can squeeze, your expected test score goes up by 0.6. That's also a linear slope. We didn't need a quadratic one. That is significant as well. What happens if you're a chick? That's the one group. It's down, unfortunately. There is a gender gap, as I would call this. So women are the one, which means they get the slope applied to their score. So women are lower by 3.6 relative to men. What happens if you are eventually going to get dementia? Lower. And if you have it already, even lower. Yeah. So all of these terms would use which of our three labels? Bivariate marginal, unique marginal, or unique conditional? Say we can rule out bivariate, right? Because there's 5 things here. And bi stands for 2. So unique, conditional, or marginal?
Marginal.
Marginal was 1 vote. Anyone else want to weigh in?
I'll second that.
Okay, 2 votes for marginal. Marginal synonym means unconditional, means applies to everyone. Marginal is correct. So each of these is controlling for the other. That's the unique part. This is what age brings to the table that grip, gender, and dementia don't have. This is what grip brings to the table that the others don't have, the unique part of the Venn diagram. So they're all unique. They're all, after controlling for everything else, this is what brings to the table uniquely. But this is the age slope regardless of your gender, of your dementia group, of your grip strength. This is the grip slope regardless of your age, of your gender, of everything else. So that's what the marginal part means. So this is an additive model, not a multiplicative model. Main effects only. Okay, how are we doing? Zoomers, doing okay? Thumb check?
Still have 2.
Still have 2. That's good. Not what I intended, but it's that point in the semester where you got to kind of look down. Am I dressed? Do I have all my limbs? Like, all that kind of stuff. All right. Then what the missing contrast here? Do I know about the difference between future and current from this model? Could I know that?
You could.
Might I want to know that?
You may.
I bet I do. So that is in R, a GLHT statement. Let me zoom back out so we can try to see everything at once. These values, what do they do? What's the logic of this?
Those are the multipliers?
Multipliers, that's exactly right. And how do I know where to put the zeros and ones? Depending on what you want to estimate, but once I know if I know what I want, how do I know where to put it?
The order in which you created your model?
Oh, close. Answer was the order in which I created the model. R will rearrange your model against your will. It is the order in which it shows up in the output.
Oh. I stand corrected.
I learned this the hard way. Because when we add interaction terms, R is going to insist that they're at the end, even if you put them sooner.
Interesting.
And I searched for about a half hour trying to figure out how to fix it, and I came up empty, and I'm like, fine, I'll just put it at the end. So anyone on the YouTube, if you know how to fix it, please tell me. I'd love to know. Based on the model order of the effects. So beta 0 refers to that 0, because I don't need a beta 0 if I'm interested in testing the difference between these last two groups. What I need is -1 times beta 4 and 1 times beta 5. That is a roundabout way of saying beta 5 minus beta 4, which is the difference between the two. So if I have -16 versus -5, the difference is that -11 there. And there's my hypothesis test, my new little function here that adds the confidence intervals as well. Okay, not so bad, right? For homework 6. Next question.
Lots of stuff.
I am interested in determining whether the effects of age and grip strength differ between men and women. That's my question. To answer said question, I need 2 new interaction terms. So does the effect of age vary by gender is answered by beta 6. Does the effect of grip vary by gender is answered by beta 7. Note that it's the centered versions that are being used here, so it all is internally consistent. I'm showing the centering in the equation so that I know, based on just looking at this, what everything means. So for instance, this is my gender effect, right? Is that the end of the sentence? No, this is the gender effect conditional on the variables that it's interacting with being 0. So I need to know where 0 is. So this is going to be the gender effect for an 85-year-old and the gender effect for someone with a grip strength of 9, because that's when those two terms would drop out, and only this would be the gender effect. So the centering, it becomes really important in these models to know what stuff means. Okay, and I do have output in both packages, I think. Yes, I did, because I knew, because this was for homework 6. That's why. So in Stata, you have seen this before, I think. You do not need to make the interaction variables necessarily. Stata will make them on the fly by this joiner here, which is either a # if you are old or a hashtag if you are not. Take your pick. I call it a #. Hashtag #. It is the thing above the 3.
Tic-tac-toe.
Yeah, exactly. Okay, so my F is significant. That must mean that my new interactions are significant, right? What do we think of that logic? This F is significant, ergo, my new interactions helped.
That's your model. That's the full model, is it not?
That's right. The 7 is your clue. This is the F for the model. And I now have 7 slopes in my model after adding these 2 new ones. So this is another point. So the slopes versus variables distinction earlier, I still only have 3 variables or 4 variables in my model. I have age, grip strength, gender, and dementia group. But now I'm up to 7 slopes. And foreshadowing what's going to happen, my F used to be 42, I think, and now it's down to 30. It got worse. I added stuff and it got worse. Why?
Well, can Can I take a guess?
You can make a guess.
Well, the residual for your model looks like it's very similar to what it was before,
Mm-hmm.
but because you have more things predicting, that means that it's not predicting as well, I think.
Yes, exactly. So the residual variance is basically unmoved from where it was before. The R square is basically unmoved as to where it was before. So what happened is that we added 2 new terms that did diddly squat. There's a technical term for you. Nothing.
They didn't help.
They did not help. And so F is per slope. So F came down because this is like the average contribution of your 7 slopes is lower than the average contribution of the 5 slopes we had before that didn't suck. So that's what this is foreshadowing as to what's going to happen. So do the 2 new interactions improve the model? I need another F because I added 2 things at once. I can't just look at either of these p-values to answer the question. So to do so in Stata is a test statement. The logic here is you tell it what you want each slope to be tested against, and in this case it's 0. So this is saying give me a joint test of these 2 slopes both being 0 at the same time, and tell me how much worse that would make my model if I didn't have them. So what do you think? My F is 0.81.
That's really small.
And the probability is 0.44.
That's really high.
That's really high. So relatively speaking, F is supposed to be a ratio of what you know to what you don't. This indicates that we actually know, like, we don't know more than we know, because the ratio is under 1. And if the 2 slopes were truly 0 in the population, we would get the ones we found, or larger, 44% of the time. So well within expected territory of the goalposts here for these 2 slopes. So this is the contribution. This is the test of the contribution to the R square for these 2 new terms jointly. The effect size that goes with it is computed using the difference from the relative previous model. So this new model is, what do we have now after adding the 2 slopes minus what we had before. So I have saved the sums of squares for the previous model as this object. So it's going to put that number in here and do the math for me. And this is the result of this model that it has also saved. I can then compute partial R square in case reviewer 3 wants you to report that. And the smarter reviewer, of course, will want you to have semi-partial R square because they don't like cheating. Semi-partial R square has another definition. 0.002. That's the effect size for my 2 new slopes. It is also the change in the R square. That is what semi-partial R eta squared means. How much of the R square are these 2 slopes responsible for? Well, I can take the previous model R square and compare it to this one, and this is the difference. So in your homework 5, I asked for change in R square because that is easier to compute. It's more direct, but that is semi-partial eta square. That is the same thing. So putting this all together, as a set, these 2 new interaction terms added 0.002 to the R square, which is not significant. But in your life, you may have significant interactions, and I don't want you to be afraid of them. So we're going to interpret them anyway with the numbers. Okay? Because not significant, don't care, don't make me do this is not a valid answer in my book. All right. Let's do the Stata output this time since we did the R output last time, but it's pretty much the same, other than coefficient versus estimate or whatever. So my constant, that's my fixed intercept. It's still about 29. Has it changed interpretation? You zoom the numbers way in here. Do I need to talk about it differently? Last time it was the expected cognition outcome for an 85-year-old who can squeeze 9 pounds, who's a dude who's not going to get dementia. Is that still the case?
Yes.
Yes, yep. So the intercept is conditional on the predictor values being 0, not necessarily what terms they're involved in. Right? The only time the intercept changes interpretation is when you add new information to the model. These are new slopes based on existing information. So I'll say that again. The intercept changes interpretation when you add new information, new variables to the model. All we've added are new slopes with the existing variables. Cheers. I didn't bring soda again today. I'm hacking my health. Okay, now with vocabulary time. Let's start with the middle 3 here. These are all unique effects, right? Gender and dementia group. Are they marginal or are they conditional? Do they depend on other variables in the model? Is my question. Or is this the gender effect for everybody and the dementia effect for everybody? Yes, because they're not in the interaction terms. So these are still marginal, unconditional. Now what about age and grip strength? Or excuse me, I messed that up. I just said that wrong. Somebody tell me why I'm wrong.
Isn't gender one in the interaction
Thank you.
terms?
I meant to do that. I totally meant to do that. No. This one is in the interaction terms. I screwed that up. So because it's in the interaction terms, is this marginal or conditional?
Conditional.
It is conditional. I highlighted too many things. How about the dementia groups? Are they marginal or conditional? These are marginal. The dementia is not in any interaction terms, but gender is. My head was in the next problem. I apologize. So age and grip and gender are all conditional because they're part of these interaction terms. So in order to know how to interpret them, I have to know when the interacting variables are 0. So age and grip are both conditional on the same thing. Who are they for? When the interacting predictor is 0, which is for men. So age 85 and grip 9, these slopes are now conditional. They are specific to men. So not just unique. Everything in here is unique. Everything is controlling for whatever else is in the model. But these are beyond that, specific to men because of the interaction terms. So in men, what happens as you get older? Cognition is lower. In men, what happens if you're stronger? Cognition is higher. Okay. Now, do you remember the 4 kinds of interactions? Interactions take their constituent main effect slopes, and they do one of 4 things. They make it more positive, less positive, more negative, or less negative. Okay. So if I'm talking about the slope of age in men is negative, what happens to it in women? I have a negative age slope as the main effect. I'm using gender as my moderator. So the interaction with gender does what to the effect of age?
You get more, less cognition.
So this one's negative, so it has to be more negative or less negative?
More negative.
More
More
negative.
negative.
Stronger or weaker in women then? Is the effective age stronger or weaker in women, given that the interaction term made the age slope more negative? Stronger. Age is more bad for you if you're a chick. Gender is a risk factor for the harmful effects of aging. How's that? So I know from the output right now that this age slope in men is not significant. I know that the difference between men and women in the age slope is not significant. Do I know if women would have a significant age slope according to this model?
One more time?
One more time. Okay, here's what I know. I know, let me back out a little bit so you can see the p-value column. I know from this right here, we said this is specific to men, right? So I know that the effective age is non-significantly negative in men because my p-value is 0.221. The interaction term tells me the difference in the age slope between genders. More specifically, it tells me how the age slope differs in women. But I don't know what the age slope is in women yet. Now I can do the math. 0.23 plus 0.29. Say it louder.
0.52.
0.52-ish. But I don't have a hypothesis test for that.
No.
Can I get one?
Yes.
I could do anything I want. Of course I can. Do you know how I was taught to get them before in my undergraduate and graduate work?
Toss a coin.
Nope. I was taught, hey, recenter gender, make the other group the one, and then rerun the model, and then you'll get the age slope for women. That's how I was taught.
It works.
It does work. It's brute force, but it works. Now, where that gets annoying is trying to cobble together all the results from different models and remember what means what. Future you will not be happy with that strategy. So I will show you how to get the age slope for women in just a second. Okay, with me so far? Any of that you want me to repeat or say differently? Okay, so for those of you on YouTube, this is proof that I do not edit my videos. It's 5 mouse clicks to put it up after class. I leave the errors. I leave everything in. Because I am not a YouTuber, I'm an educator. I'll leave the YouTubing to my son. That's what he wants to be when he grows up. I'm dead serious. He thinks he's gonna grow up and be Mr. Beast and make $1 million while people watch him play, Fortnite.
Or watch him watch people play Fortnite.
Yeah, because he watches people watch people play Fortnite.
That's what I'm saying.
Anywho, okay, let's do grip. The grip
Yes.
strength slope in men is a positive 0.7.
Mm-hmm.
What happens to it in women?
Becomes less positive.
Yeah, I've got a positive grip slope. I've got a negative interaction term. So in women, it is less positive by 0.17. But I don't know what it is in women. I just know that it's less. So I know that in men, grip strength is significantly uniquely related to cognition. I know that in women it is less related, although non-significantly, but I don't know what it is. Now I can do the math. What's 0.7 minus 0.18? 0.7 minus 0.18. Other way. I'm not doing math in front of you.
Approximately 0.52.
Approximately 0.52. So you can figure this out, and that's how you know that your code is right. Because you should get that number back. And your code will give you the standard error or the p-value.
Interesting, it's close to the sum of the other two. Except opposite.
Yeah, so the coefficients here, the standard error is next to them. That's your clue as to how different than 0 they are. So if this interaction term were 0 in the population, I would get a value this big 57% of the time. This is because there's a lot more uncertainty. The standard error is actually bigger than the coefficient.
Cool.
So let's get the missing pieces of information then.
Okay.
Here's the logic. If we want to know what the age slope is for any value of the moderator, I go into the equation, I find all the terms that have age. So if I go back up here, Do I need the intercept if I'm looking for an age slope? Nope. Do I need this?
Yes.
Do I need this?
No.
Do I need this?
No.
Do I need this?
I.
If I'm looking for the age slope.
No.
Nope. Do I need this? Yes, I do. Do I need this?
No.
Okay, I only need two things. I need beta 1 times age, and I need beta 6 times sex times age. Step 2, factor out the variable the slope is for. What's left are your ingredients to make your simple slope. So yes, a slope that is conditional on a value of a moderator is called a simple slope, even though it is the least thing from simple I can think of. Conditional would be a better word. Like, you can find a slope that is specific to a person with this value of the moderator. Same thing with grip. I'll spoil the surprise, it ends up only having two terms in the same way. And if I factor out grip, then here's my ingredients. So these lincoms then are filling in the values that multiply the betas. So in data first, actually, there we go. When I type age 85, I am referring to beta 1. Hey, Stata, can you go figure out what beta 1 is and stick that here? That's what you're saying. And I need one of them because there's an implicit 1 here multiplying it. I don't actually have to type this, but I'm typing it to make it comparable to how it is in R and SAS. Now, if I want the slope of age for men, then I would plug in the code for men into this spot right here, but that's a 0. So it turns out that I didn't actually need to write this one because this is not a linear combination. I already have it. It's up here. That's it.
Yay.
Now, why would I do this? Number 1 is pedagogy. Number 2 is that sometimes it's helpful to have everything you want in one section of the output as opposed to having to like search across different tables to pull things together. For women though, I need one beta 1 and then I need to put a 1 in here, which then activates beta 6. So that is indeed a linear combination, and that's the one I don't have yet. And lo and behold, the slope for age for women is exactly what we thought it should be if you add the main effect and the interaction term together. And it is significant.
Which is different than what we looked up above.
Yeah. So putting that all together, what we have learned is that age is not significant in men. It is not significantly different in women, yet it is significant in women. Keep in mind that the power to detect these things changes. Because this is specific to men, the number of men in my sample are going to dictate the power for this simple effect. And the number of women in the sample would dictate the power for the age slope in women. So you can end up with things changing their relative significance because they're based on fewer cases. They're conditional to specific kinds of people. Same idea for the grip strength slope. The one for men, I actually didn't need to write because if I fill in 0 here, it's not a linear combination, it's just the main effect of grip from up above. And the linear combination I do need is for what it is for women. So the grip strength slope in men plus how it differs in women gives me this 0.52 result, which is significant. So grip strength is related to higher cognition in both genders, and the interaction term says these two numbers are not significantly different. That's what I've learned. So the answer to my research question is, does the effective age and does the effective grip strength vary by gender? No, it does not. I've got all the pieces now that I can do that. Now, who here is like, what? Is that accurate? So is your reader. So the critical important part is, as shown in figure 1, make them a picture. Here are some pictures. So in Stata, you can easily ask for predicted values for a range of things. So what I'm doing here is asking for predicted outcomes. That's what margins does. At is I'm putting in the values of the centered predictors. So I am holding dementia constant at 0 because my goal here is to show the two interaction terms, and dementia is not part of that. So this is just for the none group because the pattern would not change. The range here, the first number is where it starts, the second number is the increment, and the last number is where it stops. So I'm asking it to plug in -5 and 5 for age, and that would give me a prediction for an 80-year-old or a 90-year-old, given the centering at 85. I'm holding grip strength constant at -3 because this plot is just going to show the age by sex interaction, and then I am asking for predictions from 0 to 1 in increments of 1. Then I'm telling it, make a picture with this information and use age as the x-axis. And here it is. So the predictor that we care about is on the x-axis. The moderator is shown by different lines. So what we've learned is that the blue line was not significant. The slope of it, that's for men. The red line slope is significant. That's for women. But the difference in the slopes is the interaction term is not significant. So when you look at the picture, the idea of more negative in women works. Goes down more. Age has a bigger impact in women, but non-significantly bigger. So interaction terms are non-parallel lines. If you try to make a picture with an interaction and the lines are parallel, something went wrong. The other way we can talk about this is to think about gender as the predictor we care about and age as the moderator. So let's go back from that perspective. This is the gender difference for what kind of person? Let's spin it the other way. Given the interaction terms, this is the gender difference in what kind of people? Age 85 and grip strength 9. In those people, women are lower, significantly. What happens to that gender difference in older people? More positive, less positive, more negative, or less negative? More negative. So is the gender effect bigger or smaller in older people, according to these values? It's bigger. More negative or more positive means it's bigger. So age exacerbates the gender gap. And I would use those words. Like a gender slope is not a meaningful thing because there's only 2 in this binary variable. You would need additional predictors if you wanted to have other categories. But a gap is a word that implies a difference between 2 things. So the gender gap is the thing we're talking about. That gender gap is larger in older people. It is also what in stronger people? This is another more negative. So, yep, grip strength also exacerbates the gender gap. And so if we approach it from that perspective, the other way we can look at this plot is as the difference between the lines. In men, there is, the difference in younger people, the difference is smaller than in older people. Age exacerbates the gender gap. The gap is the difference between the lines. Grip strength exacerbates the gap, the difference between the lines. So these kinds of pictures are essential if you're going to present an interaction term and talk about it. Because then you can say things like, the slope of age is given by the model is for men is the blue line. Like that's your main effective age. The difference in the slopes is your interaction term, and then the linear combination is the slope of the red line. Same thing over here with respect to grip strength. All right, that's all the Stata stuff. Our folks are gonna have to wait till Thursday. I know. But all good things must come to an end. Including this class. I know.
No, it continues next semester.
Yeah, well, I'll be back. I'll be back on Thursday. Before then, though, we got this semester to wrap up first. All right, any questions or comments as we wrap up for today? It's not so bad, right? It's complex, but once you get the hang of it, it's not so bad. We'll keep working on it. All right, thanks for being here. Let me know if you need anything. And feel free to start your next homework if you feel like it, or ignore me if you don't. It's fine.
Is the mixed quiz due Monday?
Nope, nothing is due Monday.